All right, so this is going to be the answer key for the scientific notation practice problems worksheet on ClassKick. I'll be showing you just the answers, and I'll go through each slide and let it sit for a few seconds and then move to the next slide. That way, if you just want to check your answers, you can pause the video, see the answers, check off the ones that you got right or wrong, and then I'll go through each problem individually with the walkthrough of how to solve the problem along with, of course, the answer. So here's the first slide. These are just converting standard notation to scientific notation. I'll leave that up for a couple of seconds. You can pause here. And here's the next slide. This is converting from scientific to standard. Pause here. And the last two slides are doing calculations with scientific notation. Here's multiplying or dividing. So you can pause here to get these answers. And then finally, you can pause the video to see the answers. These are addition and subtraction of numbers in scientific notation. So pause here for a sec. All right. Now I'm going to go through each problem individually. And there will be bookmarks down below, so you can jump to whichever section you need to check. If you want to check just the answers for the addition and subtraction, go down below. There'll be a link that picks the video up right at the beginning of that section of answers with the explanations, so you can jump around as needed. All right, so the first problems are converting standard notation to scientific notation. So remember, the key is that we want to have a coefficient, so that's a number between 1 and 10, as the first part of our scientific notation, and we need to move the decimal point around so that we end up with only one digit to the left and any other digits are to the right of the decimal. So in this first example, the decimal point, which isn't written, but it's understood that it's right there. So in order to get it so that I only have one digit to the left of the decimal, I need to move 1, 2, 3, 4 places, and now I have 6.15. That's a coefficient between 1 and 10. So that tells me I've put the decimal point in the right place. Times 10, that will always be the case for scientific notation. And then we need an exponent, or power of 10, which is determined by the number of times I had to move the decimal place in order to get my coefficient the way I wanted it. So in this case, it was 1, 2, 3, 4 times, so the power of 4. Common errors are people will stop at the zeros, or they will not count all the jumps, or maybe count one too many and go all the way to the left. Those are things to look out for. The other thing to be aware of is that a positive exponent means we started with a number 1 or greater. If it's a negative exponent, as we'll see in a minute, that means we started with a decimal, or a number less than 1. All right, so the second example, the decimal point is here. It starts out here, and in order to get it to one digit, 1, 2, 3, 4, move past the 5. Now the decimal point is between the 5 and the 6, which means I have a coefficient between 1 and 10. I keep the 0.68. I can drop the zeros that came before that, and then it's times 10. The exponent is 1, 2, 3, 4, 5 moves, and because I started with a decimal, I use a negative exponent, negative power of 10. Next one, decimal point is here. I move 1, 2 places to get the decimal point between the 3 and the 2. And it took 2 moves to get from the start to the finish, which means my scientific notation here is 3.21 times 10 squared. And I realized that writing this in scientific notation actually took more work than just writing 321. The fact is, most of the time, we won't be working with numbers that are this close. But be that as it may, as we'll see later on, even if the exponent is 0, like we had a single digit number to begin with, then if you're asked to give the answer in scientific notation, you have to write it that way. So you need to be able to work that out no matter what the exponent is, no matter how big or how small, positive or negative. All right, number 4, to move the decimal point once, twice, 3, 4, 5, 6, 7 times to get it between that 6 and the 4. 6.496, and I drop the zeros, times 10 to the 1, 2, 3, 4, 5, 6, 7 power, and it's positive because we started with a big number, more than 1. And then the last one here, this is a decimal, so we're going to have a negative exponent. Anytime it's a decimal, you know it's going to be a negative exponent. So we move once, twice to get past the 7, so that I have the 7 to the left of the decimal. Everything else goes on the right. And it took 2 moves to get there, 2 places. So -2 because it was a decimal. Now, as far as the digits, right, some of these have 3 decimal places, some have 1, some have 2. Actually, some have 2. There aren't any that have 1. But the point is, with these numbers, there's no rounding involved because I'm not calculating, and we can assume that these, because they're all non-zero digits, that those are significant. Down here we had that sandwich 0, that's significant, but all the other zeros get dropped off because they're just placeholders. Okay, so when you convert to scientific notation, one of the big reasons we do that is to get rid of those placeholder zeros and simplify the number. All right, moving on. Here we're converting from scientific notation into standard notation. So we're expanding the number, adding decimal places, adding zeros as needed, depending on what the exponent tells us to do. So 10 to the power of 3, 10 cubed, means we're going to move the decimal point 3 times. And since it's positive, that means we're going to make the number bigger, which means we have to move the decimal point to the right. So we start out with 1.09. And I got to move 1, 2, 3 places, fill in that extra place with a 0. That's what the placeholder zeros are there for. So that is your positive 3 exponent. 1, 2, 3 places to the right. That gives us 1,090. Okay. The next one is to the power of 8. So that means I'm going to move the decimal point 8 places. It's a positive number, so I'm moving it to the right. I'm making a bigger number. So 4. The decimal point was already past that, and then it's 1, 2, 3, 4. Now I have to add zeros. 5, 6, 7, 8. Shlemiel, shlemazel. All right, so there you go. We added 8 places. 4 of them were zeros. 4 of them were digits that were already there. Did I mess that up? 1, 2, 3, 4, 5, 6, 7, 8. I did. I added an extra 0. I always said adding, I've already said adding and missing a 0 can make a big difference, which they sure do here. So it's really 422 million. Okay, so 8 places, I did 9. So you got to catch yourself, check yourself before you make those mistakes. Scientific notation is negative this time, which means I'm going to end up with a decimal. So I have to move the decimal point to the left. So 3.078. I move the decimal point once, 2, 3, 4, which means, just to clean it up over here, 0.000378. Okay, we add those placeholder zeros. This one, that's just there to kind of highlight the fact that there's a decimal point there. That's not one of the jumps, but just so if you didn't have that 0 there and you wrote 0.000, that would be fine. I always put that there just to kind of highlight where the decimal point is, because it would be easy to miss. If you're writing it out and there's just a little dot there, it might be easy to miss. Okay, next one, -2. So we're going to end up with a decimal. So if I move this decimal point over twice, I have to add a 0 after the decimal, and then 9004. Last one. This one is 10 to the second power, positive, so I'm going to make a bigger number. So 5, and then 2 places, 1, 8.74. So this is a case, we haven't seen an example like this before, where the number, even after we expand it, is still a decimal. Okay, we didn't even have to add any zeros because there were more digits than places we had to move. So, that can happen. It doesn't happen all the time. But there's no rule that says you have to add zeros. If you move a certain number of places and you still got digits to work with, well, that's what the problem requires. All right, so we're going to move on to the next one. This is multiplication and division. So remember, with multiplication, you're going to multiply your coefficients and then add the exponents. If it's division, you divide the coefficients and then subtract the exponent. So you subtract the second exponent from the first, or if you set it up as a fraction, you subtract the bottom from the top. So let's take a look at these. We've got, if we go through this, we've got 2.8 times 3.16, and then that's going to be times 10, and it's 7 plus -3 for the power, for the exponent. So the coefficient becomes 8.8, and I'm rounding this because the coefficient in that first number only had 2 significant figures, so my answer can only have 2. And then it's times 10. 7 plus -3 is +4. So 8.8 times 10 to the 4th power. Here we have division, so I'm going to do 9.12 divided by 3.8 times 10 to the -5th, that's the first exponent, minus 6. Because we're dividing, we subtract, and we're subtracting from a negative number, so it's going to be even more negative when we're done with it. So when we do the division, again, rounded to 2 digits because 3.8 only has 2 digits. It's not 2.8, 2.4 times 10, -5 minus 6 is -11. So again, what happens here, just in terms of kind of thinking through the logic of this, the fact that this was a negative exponent means that this number written in standard notation is a decimal, and that's on top of your fraction. The bottom number is a positive exponent, which is a really big number. So we're dividing a decimal by a really big number, which creates even more of a decimal. So the fact that it became -11 makes sense if you kind of think through what we're doing in the actual calculation. All right, division again. So we've got 6.2 divided by 1.9 times 10 to the 3 minus 4. Okay, so that equals 3.3, which makes sense, to the times 10 to the -1 power, -1st power. 3 minus 4, you get -1. Okay, the exponents don't have to be big or small. They are what they are. That's another one of those things that throws the kids off sometimes, like, well, how can my exponent be that big or that small or that positive or that negative? The numbers aren't concerned with how big or small they are. Just work through the steps, and the answer is what it is. Okay, multiplication. We have 1.5 times 6.25 times 10 to the 4 plus -3, 3rd power. Okay, so we do that out, and we get 9.4 times 10 to the 1st. Last one on this page is 5.06 divided by 2.2 times 10 to the 6 minus 5th power. Okay, so that comes out to 2.3 when we divide the 5 over the 2, and times 10 to the 1st again. So again, these exponents could be 1. We'll see, I think on the next slide, there's some that are 0, and that happens. It is what it is. If it's supposed to be in scientific notation, you have to put the times 10 with the exponent, even if that exponent is 0, which would mean it's times 1. Okay, so these are addition and subtraction problems. The key with the addition and subtraction is that your exponents have to be the same before you can perform the calculation. So in the first example, in fact, in all but one of these examples, I think, we're going to have to make some adjustments to those exponents. We've got 4.73 times 10 squared plus 9.3 times 10 to the 4th. Those two numbers are not equal values. The first one is 473. The second one is 9,000, or 93,000 rather. Okay, so you can't just add the 4.73 and the 9.3 because they're not even close to the same place values. So we have to move the decimal point, And I always say move the smaller one to make it bigger. So I'm going to make this 0 point, since there's a difference of 2, I have to move the decimal point twice. So 0.0473 times 10 to the 4th. That is the same number as 4.73 times 10 to the 2nd. I haven't changed the actual number. I'm just adjusting the value of the exponent so that then I can add these two numbers together fairly, right? Because the 473 times 10 to the 2nd, 4.73 times 10 to the 2nd, is much smaller than 9.3 times 10 to the 1st. So I have to move that decimal place over to make it line up properly. Okay, plus 9.3 times 10 to the 4th. Now I can add the coefficients because the decimal place will line up properly if I were going to sort of stack those and add them. And then it's times 10 to the 4th. Okay, the exponent stays the same. You don't add the exponents when you're adding scientific notation. You add the exponents when you're multiplying in scientific notation. So this becomes 9.3473 times 10 to the 4th. Now, here's the trick. Because the 9.3 we started out with only had two significant digits, my answer can only have two significant digits, which means I'm going to round it here, and the result is actually 9.3 times 10 to the 4th when it's properly rounded. So you might be saying, well, we started out with 9.3 times 10 to the 4th, and we ended up with, how did we add anything? The point is that you added a number that was so much smaller than the number that you started with here, 9.3 times 10 to the 4th, that it doesn't make a significant difference. Because when we write these out, these zeros here aren't significant. So I added the 473, but I don't know, from a measurement point of view, I don't know what the value of those zeros really could have been. The 9 and the 3 are measured values. The 3 zeros there are placeholders. So I can't say with any certainty that it really is 9.3473, because any one of these zeros could have been some other value which would have changed all of these digits. And so because of significant figures, we round it off. And this will happen occasionally where you're adding a really small number to a really big number. In the sort of scheme of things, you aren't affecting that really big number enough to change your answer. It's just one of those things that will happen sometimes. So this is the final answer here. The next one, we've got 7.6 times 10 to the 6th plus 3.6 times 10 to the 5th. I have to increase the exponent here by moving the decimal point over 1. So I end up with 7.6 times 10 to the 6th plus 0.36. Again, that 0 is just there to highlight the decimal point. And now this is times 10 to the 6th. So now I can go ahead and do my calculation. 7.6 plus 0.36 times 10 to the 6th. The exponent there doesn't change. So we end up with 7.96 times 10 to the 6th. And then if I round that, we have two digits here, so our answer can only have two digits, which means I'm rounding here. Since this is a 6, this becomes a 0, and that becomes an 8. But because I have to have two significant figures, I keep it as 8.0 times 10 to the 6th. This is an example, an important example of where the 0 is significant. I'm going to keep it in my scientific notation to show anyone looking at this number that that 0 is a significant digit. If it wasn't, it would just be 8 times 10 to the 6th. Next one. These two, okay, these two numbers here have the same exponent. So I can just go ahead, and since it's subtraction, I can go ahead and do 4.6 minus 6 times 10 to the negative 1, which is negative 1.4 times 10 to the negative 1. So we got a negative exponent and a negative number. It can happen. Okay, when you subtract something big from something small, you get a negative answer. And the fact that this is a negative exponent means we were actually subtracting decimals in the first place. But either way, If we wrote this out, it's 0.46 minus 0.6. So we should get a negative number, which is what we did, which in standard notation would have just been 0.14. Okay, so that's how you get there, and negative 0.14. Next one, we've got a 0. Here's a power of 0 and a negative 1. You've got to change one of those exponents. I always say make the smaller one bigger. Keep in mind that negative 1 is smaller than 0. So this is actually the number that we're going to change by moving that decimal point over 1. So it's 3.4 times 10 to the 0 plus 0.44 times 10 to the 0. Add your coefficients, 3.4 plus 0.44 times 10 to the 0, which is 3.84. Two digits. I got to round to two significant figures, so 3.8 times 10 to the 0. Again, what does that mean? It means that the answer is 3.8. But if the answer has to be in scientific notation, you have to write it times 10 to the 0. That's just the way the scientific notation works. All right, last one. 6.7 times 10 to the third minus 8.6 times 10 to the first. 10 to the first has to become a bigger exponent. So it's going to be 6.7 times 10 to the third minus, because this is a difference of 2, I've got to move the decimal point over 2 places. So I end up with 0.086 times 10 to the third. And again, that's the same number as 8.6 times 10 to the first. And we've got 6.7 minus 0.86 times 10 to the third. That equals 6.614. I have to round to 2 digits. So 6.6 times 10 to the third. Okay, so again, remember, for multiplying and dividing, the exponents don't have to match. You're either going to add or subtract them, depending on the calculation, the operation that you're doing. Adding and subtracting, you must adjust the exponents so that they match before you do the operation with the coefficients. And then you don't change the exponent at the end when adding and subtracting. Sometimes if you're multiplying and dividing, if you end up with a number that's smaller than 1 or bigger than 10, then you might have to move that decimal point, once or twice usually, and adjust the exponent. That will almost never happen when adding and subtracting. Okay, so there's all the answers, all the solutions worked through. I hope that helped. Thanks.